Okay, here we are. It's the physics video lecture once again. Fluid mechanics video lecture 6. And what did we end with? Bernoulli's equation. And I'm going to give another example of that before moving on. So we're dealing with ideal fluids. And let's imagine we have wind here. We've got a fluid flow over a street, and there is a canal underground here. So this is the street level. So we have airflow up here and V equals 0 down here. Now we're pushing the little hole in the manhole cover there so that there's airflow between above and below. We're pushing the concept of a streamline a bit hard right here. But we can just call this 1 and this 2 up here. And if the y-axis difference is very negligible, let's go ahead and write this first of all. So Bernoulli's equation will have P1 plus 1/2 rho V1 squared plus rho GY1. P2 plus 1/2 rho V2 squared rho GY sub 2. So that's Bernoulli's equation. And let's let y sub 1 be approximately equal to y sub 2. Because we're just taking the immediately above and immediately below range. And then we also know that P sub 1 is equal to P atmosphere, V sub 1 is equal to 0. So we have on the left side just P, I'll write atmosphere, P sub 1. So we've got atmospheric pressure down here, and Y1, Y2 are about the same, so, and that's 0. So over on the right side, we have P sub 2 is equal, not P sub 2 is equal, P sub 2 plus 1/2 rho V sub 2 squared. And now we can solve for P sub 2. Piece of atmosphere here, P sub 2, and we're going to see that. Let's go ahead and do that first, and then we'll draw our conclusion. So P sub 2 is atmospheric pressure minus 1/2 rho V2 squared. So I'll put a box around here, kind of interesting. So first of all, you can see that the pressure is going to be decreasing. We're above here, higher pressure below, so a high wind speed, we can actually imagine this cover just being blown up or knocked, launched vertically. And you could calculate the pressure differences times the area would give you the force. And those numbers would already show considerable force. So if you take this naively and you have say a 1 square meter here, you're gonna have a tremendous force pushing up. So that's the first application. The second application is if you just take this to a limit. What if the speed is sufficiently great so that the pressure vanishes? And in fact, since the speed here isn't restricted, what if it's so great that the pressure becomes negative? Okay. So is it possible to have negative pressures? Question. P sub 2 less than 0? Question mark. Well, at any rate, there's a critical speed. We would have V sub 2 would be just the root of 2 atmospheric pressures divided by the density. And I'm going to leave it right there. Less in gases, but in liquids, this actually plays a big role. There's a phenomenon called cavitation. And those negative pressures can result in dramatic damage, say, to propellers in a ship, propellers, that type of thing. So I'll just put that word down for you guys to research if you're interested. Cavitation is the phenomenon here. I'm just going to put a question mark. You guys look that up. You see where it comes from. An elementary discussion of Bernoulli's equation already brings it into play. And these speeds aren't even that high because you're looking at, of course, you're looking at twice the atmospheric pressure divided by the density. Well, that's 10 to the 5, but that's 10 to the 3. Okay. Good. So yeah, that was the last interesting example of where Bernoulli's equation can lead you. So we're going to leave that. I recommended last time too, just look up what your general physics textbook has on Bernoulli's equation if you want some more examples. We've talked about a few now. So where we're headed now is back into the technical discussion. Our next topic is Euler's equation and the conservation of circulation. Euler's equation and the conservation of circulation. So we have to look at circulation. This is our technical term. Circulation. And we'll just define it. It is the line integral around a closed curve of v dot dl. Okay, just the line integral of the velocity field dotted in the path around a closed curve. So that's the circulation. And we want to see where this comes into play. So first we'll start with Euler's equation. Or actually, let's do some examples that we've already talked about. So if we had in our rotating bucket omega cross R, call it V1, or V equals omega cross R over R squared. And we know that if we're looking at our omega right here, that we've got that literally circulating fluid, and the here gamma would be equal to integral v1 dot dl. We did that one, and in fact for this one right here we just ended up with 2 gamma constant here, and that was actually regardless of which path we took, as long as we were going around the omega axis there. Okay. Now let's look at Euler's equation. So this was just a concrete example. Point is, we could form this integral in any fluid flow. I'm going to write Euler's equation down in a couple of forms. So this is the one we always start out with: dv dt v dot gradient minus gradient of w minus 1 over rho gradient p plus g if you prefer. Right, but this is a nice simpler form. Also, when we took the curl we had d dt curl of v was curl of v cross curl of p. That was another form of Euler's equation. So what we're going to do is consider the circulation, which we've now defined here, of just some fluid element. So now consider this circulation or just some fluid flow, and we can visualize that, you know, we're doing a little integral. I'm going to use a different color. Doing a little integral around here. So we've learned about streamlines, and we can be doing a little integral around, say, a straight line. But it wouldn't have to be that, but that's an example. Okay. What we're going to ask, though, is what happens to this quantity in time, say, as the water elements are carried down along the streamline. Or a flow, as in the picture, what happens to the circulation as the flow carries an element along, along a streamline. An element, maybe I should say a fluid element, how about that? Question mark. So of course, mathematically, we're just looking at what about this d omega dt? So what happens there? And what we're going to do is a time derivative of this quantity here. So I'll just write this down and then explain a bit. So we're looking at the time derivative of this integral v dot dl. So I'm just going to introduce some symbols here. I think the best thing to do is go into the integral right away. So we're going to have a dv dt dot, and I'm going to replace dl with dr. Okay, I'll replace it right here as a matter of fact. So we can call it what we want, right? dr. But I'm going to write this as a dr plus integral v dot ddt of this dr. So what I'm doing is just differentiating between time derivatives for which I use d and spatial derivatives for which I use this del. Okay. So use d for time, this del for space. Other than that, I've just done a product rule under the integral. So let's continue on with this. Okay, so directly underneath here, we've got this d omega dt. Now the second integral, I can exchange the time and the spatial operator, and so I have integral v dot dv like this, and this is the total differential of 1/2 b squared, and the integral of a total differential around a closed path equals 0. Equals 0. Total differential around a closed path. So I'm just left with this right here. Okay, so there's a couple of ways I can deal with that one. Okay, but let's bring this over here. So now it's equal to, and Euler's equations are up there, that's good. So that's equal to this integral dv dt dot, actually, keep going with this. Okay, what we're going to note next is that this complete time derivative is really the entire left side of the Euler equation. Remember when we transformed to the field point of view, we went from here to here, but now we're asking about the element of water being carried along. Okay. So this thing can therefore be replaced with the right side of this equation here. Okay, so this is all dv dt, so it's just minus gradient w dot dr. One hand, let's hold on to this. We can actually do something else here, line integral, so we can actually say, we'll use that in a moment. So this is a line integral, so we can actually say this is the curl of this dv dt. This is what we wanted. And at d area. So this would be an area, and this would be the boundary of that area. Here, let's leave this one off for the moment. Now I'm going to make use of the gradient. Okay, so I've got the curl of dv dt. Here's my argument. This is the left side of Euler's equation. So now I'll get the minus a curl of gradient w dot n hat dA, and now what do you know? Curl of a gradient vanishes identically. Okay, so this is actually 0 equals 0 exclamation. Okay. So apparently the circulation remains constant as water is carried along streamlines. Okay, circulation remains constant, and this is called Kelvin's theorem, conservation of circulation. So yeah, that's what we wanted. So Kelvin's theorem conservation of circulation. And again, that line integral is constant. writing it down one more time. So circulation V dot dl equals constant in time. Okay, so that has some interesting consequences, and what we're going to be discussing a lot coming up here is these idealizations, because there are applications of this, and then there are places where these statements break down. So that's something we want to be aware of when we're talking about ideal fluids. But yeah, here's our Kelvin's theorem. Definitely important and useful. Okay. So the first thing we'll do is look at some consequences. And then we become aware of the circumstances under which these statements hold. So we've got Kelvin's theorem, consequences. And the first one I'll just write down as an approximation. So we, of course, have this V dot dl being equal to the curl dot m hat dA, like that. Now for an infinitesimal element, so small, I'll just write small element, then we can just multiply a curl of V and a dA like that. So we have this thing here which is called the vorticity. So vorticity omega vector, that is the curl of V, and we see that it moves with the fluid. That's what we were just showing, right? It's constant as it moves along with the fluid. And as such, if you have vorticity in an ideal fluid, you never lose it. And on the other hand, if vorticity is zero in an ideal fluid, it never appears. Now that's the thing where the real fluids have a difference of opinion on, so to speak. So let me try to pull that together here. I'll give some examples. So what I just said, I'll put down here in words. For an ideal fluid, if omega equals 0 initially, then omega equals 0 always. And it's also the other way around. If it's not equal to 0, then it's not equal to 0 as it gets carried through the fluid. The reality of these statements is that they hold true, first of all, again, that fluid has to be ideal, and they're practically valid in the bulk, okay? But at boundaries, at surfaces, is where things do not hold as true here. So let's look at that as an example. I'll get a better picture of there. So the example where everything kind of plays out is just if you have the flow past an obstacle. example, we could even call it a two-dimensional flow past an obstacle. And in this case, here's our obstacle. Okay. And we have a flow, use different colors, coming around like this. Okay. And these can actually be exactly calculated. So the flow around a cylinder, when we say two dimension, the two dimensions we're looking at, the third dimension is out of the board, and the field is uniform in that dimension. Okay. So yeah, suppose you have a flow like this, and if you came in from far enough downstream, that's supposed to be an infinity. Okay. And you go out here to plus infinity. Then if you're far enough away, your flow is uniform. And then if you're far enough away on this side, it's also uniform. Well, if it's uniform, then it has no vorticity, right? It has no curl. So on this right here, uniform, so omega equals curl of V equals 0. That's out in that distance. And then the idea that we just proved is that along this line, streamline here, the vorticity is 0 the whole time. Well, all of these streamlines are going to be the same if you go far enough away to the left, and yet some of these streamlines are going to go along the surface even. They're going to end up going along the surface, or they'll be very close, and then you will actually, not from Euler's equations. From Euler's equations, you can actually get a smooth flow all the way through here, no vorticity. But in reality, these surfaces, or the behavior around the surface, is not going to be that smooth, and it's not going to be vortex-free. The consequence of that is that instead of this smooth picture here, in reality, you're going to develop vortices and even turbulence downstream. So you don't have that symmetry. Okay. So again, in the ideal fluid, no vorticity here at the end, therefore, right, curl is 0. Therefore, curl of V is 0 always going through here. So ideal fluid, ideal omega equals 0 always. But the real fluid, here I'll use another color, real fluid is that little eddies are formed here, and they'll actually be carried downstream, and as you increase the flow speed, you can even get some serious turbulence here downstream. Real fluid eddies form and are carried downstream. And it's the boundary conditions that play this role. So the reason for this, I'll write this, the reason for the Euler equation, V tangent, I'll tell that V parallel does not have to be 0 at the boundary, okay, at the solid boundary. And in fact, Euler's equations require this condition, okay, in order to be consistently solved. And again, this flow past the cylinder can be exactly solved, and all these things hold true. Now, we don't yet have the real equations, so the Navier-Stokes equations, they're coming up later, but I'll put that right here. But Navier-Stokes equation, which is going to be a modification of the Euler equation, has V identically equal to 0 at a solid boundary. Okay, and this can even be illustrated here now. Suppose this is a real surface, solid boundary, velocity vanishes here, then you're going to have a gradient in the x component, right? It's going to go from 0, so the real one here, this picture's going to have a lot going on. There's a 0, right? You're going to have the speeds increasing, and in the other components as well, such that the curl is not going to be equal to 0. We'll actually calculate those later. Good. Nonetheless, we're not, by any means, we're not done with the Euler equation yet in the ideal fluids. We just have to be aware of this, right? The ideal fluid is going to have the conservation of circulation as though you actually would have some tangential components right at the surface. In reality, you don't. So that's the point of this. I've kind of mentioned these things a few times already. It's important. But in the bulk, so away from this surface, you will have this conservation of circulation and interesting vortex phenomena and eddies as they just propagate through the bulk of a fluid. But this is interesting as well, right? So also omega not equal to 0 initially, then omega not equal to 0 always, okay? So the ideal fluid has these interesting vortex theorems, but the actual generation of a vortex, of vorticity, the generation of vorticity happens primarily at a surface. That's where it's easiest to do. It can happen anywhere in the sense that there is that internal friction in a fluid, but you can generate them at a surface, but they can then propagate conserved, and that way they can propagate for a great distance in the bulk. Okay, so those are some interesting mathematical aspects. And the fact is, in physics, you have to be able to use some judgment and know when to use your equations and when they're not valid. So fluid mechanics is really rich in situations like that. Let's see, that is probably what I wanted to say right here. A couple more things about ideal fluids. Actually, we're going to be dealing with them for a while, ideal flows. But yeah, this whole discussion has a number of aspects. Right? We've got the ideal flow, the non-ideal flow. I'm going to do another version of this right away as well. So now let's treat the thing just as an ideal flow and draw some consequences here. So I'm going to redraw that picture. Flow past an obstacle. So again, we've got this obstacle. We'll try to make a neat picture. And we've got the flow past it. Now it's just ideal. And I'll label this point A and this point B. So regardless of the flow elsewhere, we can be sure that you could have something like this, right, going around here. But right at these points A and B, V is definitely equal to 0. So again, ideal flow V at A equals V at B equals 0. So what would Bernoulli's equation tell us? And of course, when we have these kind of streamlines, we're thinking time independent. Okay? There's no time dependence on these, it's fixed picture in time. Bernoulli's going to say, let's just write it out. B sub A plus 1/2 rho B sub A squared equals B sub B plus 1/2 rho B sub B squared. You know, in fact, the actual mathematical general ideal flow solution to this has the true symmetry in the picture as well. It's the same on one side as the other. This kind of even tells you why, because Bernoulli's equation was rigorous. B sub A, B sub B are 0. So this was good for, you know, symmetric situations on either side, but specifically A and B, B sub A equals B sub B, and from that you can conclude that the force on this object, even though the flow has this directionality, you can conclude that the force on our obstacle here is equal from both sides. Okay? And that being the case, therefore the net force is 0, and therefore this thing does not get swept downstream. So that's called D'Alembert's paradox. So pressure is equal, therefore no net force on the body. And that is called D'Alembert's paradox. D'Alembert's paradox. Anything else to say about D'Alembert's paradox? Yeah. Right. So there's no resistance, no net force on this thing. That's of course paradoxical, but that's what Euler's equation gives you. So if you need to know what the force is on a body due to a flow, we're going to again have to have the viscosity terms, which we haven't introduced yet, along with the boundary conditions that I mentioned as well. So yeah, and this was, the fact that it's D'Alembert's paradox means it was discovered a long time ago, but in Euler's day. This result came up. This is, of course, not what you see in nature. Okay. So yeah, it's a good one to see, and if you have Bernoulli's equation, it's that easy to generate. Okay, just this way right here. Okay, I'm going to consult the clock. D'Alembert's paradox, very interesting. So the next topic is called potential flows. I think we got a good discussion of this stuff right here. So with the understanding that these are idealizations, we move on to another very useful category of flows. Potential flows. So I can't complete that right now, so let me see how I'm going to set that up. Okay, this is great. So first of all, this is easily done. Talk about that. So if curl of V equals 0, then by the Helmholtz theorems, and we have examples where the curl of V equals 0 and where it's not equal 0, so that's enough for now, right? We've discussed that kind of at length. So the class of fluid flows where the curl vanishes are called potential flows, because then V can be expressed as the gradient of a potential. That's by the Helmholtz theorem. Helmholtz theorem. So we're going to pursue that, but first, after giving this definition, I want to give another class of flows. Remember, we did have some in which the curl was 0, so those are potential flows. But an important class of such flows so that we'll just have an important example are the flows that are generated by a small oscillation, or flows generated or produced by a small oscillation. So imagine you have some body L in size, and it's oscillating, it's vibrating, and you can imagine it's going to at least send off sound waves. It can send off sound waves, or in general it'll propagate some kind of fluid motion. So that's what we're looking at. We're looking at a solid body here that is somehow oscillating. So this body of roughly size L oscillates with frequency omega, comma, amplitude A much less than L. Okay. So yeah, it's oscillating, some tiny little amplitude change, some frequency omega. So now what we do is look at Euler's equation and do an estimation. So we've got that oscillating body, and we can imagine it sending out sound waves and any other little motion that will be propagating through the fluid. So that's the way we're looking at it. And we can draw a little bit of something there. Good. So our fluid equation is, of course, dV dt plus v dot gradient v minus gradient w. We got that simple form there. And what we want to do is estimate the relative size of these two contributions. So I'll just write that this way. So we estimate the magnitude of v dot grad like v divided by dV dt. And these are just approximations, but the derivative involved here is going to tell us that v changes appreciably over the length scale L. The appreciable change in magnitude of v happens over the entire length scale of L. So we can say we've got a v squared over L in the numerator. Okay. In the denominator, we basically have a v over tau, where tau is the time scale, and v is the, between 0 and v, the scale of the speed. So I'll do my little approximation right here. So this v over tau goes as omega times v, because it's, omega is 1 over tau and vice versa. Okay. Then we have v is, so, and omega times a is equal to v, because a is a length, omega times a length is the speed. So what do we have? V over tau goes as omega, which is v over a, times v, which is v squared over a, and remember a is amplitude. So here we have v squared over L divided by v squared over a. And that, we can cancel the v squareds, we have a divided by L. And so clearly, since this is much less than 1, much less than 1, this term dominates. This one dominates over that one. And because of that, we have dv dt equal to minus gradient of w. But now we're going to make use of this right here. So if we have, we're going to erase, make some room. Okay, so coming up from there, so dv dt equals minus gradient of w. So we can just exchange differentiations, and we can say we have gradient of d phi dt, okay, making use of this now, equals minus gradient w, or gradient of d phi dt plus w is equal to 0. But those are spatial derivatives. That means that what's in here, d phi dt plus w is equal to some function of time. And before I move on, good, that'll actually work. Actually, no, I'm missing an ingredient. Missing an ingredient here. Oh, here's what I did wrong. One take, no edit, but we caught this. We caught this. I can't draw this conclusion yet. I'm gonna have to stay right here. So actually, I now have, Okay, once more with feeling. Got a missing step here. I just plugged in what I'm trying to prove. So let's go back to what we have here. We have this, okay. The estimate was good. So now, dV dt equals minus gradient of W to adequate approximation. I'm trying to generate the fact that this is going to be a potential flow. I can't plug it in yet, okay? But what we can do is this. dV dt is minus gradient W, and I can take the curl of both sides, therefore d dt curl of V is equal to minus curl of gradient W, which of course is identically equal to 0. So that I can say. And here, of course, I've just exchanged the order of derivatives the way we do. So that means, since this is 0, that the curl of V is equal to constant. Okay. So we don't yet have that the curl of V vanishes, it's equal to a constant. But for small oscillations, the time average of the velocity will vanish. Okay, the time average vanishes for small oscillations, and therefore we can say, well, that may very well be a constant, but that constant is equal to 0. So that's the argument. For small oscillations, the time average of V vanishes, and therefore our constant, this one here, constant sub blue star, our constant equals 0. Okay, so that was the missing step. Glad I caught that. Now we have what I just had up there on the board. Now we have curl of V equals 0. Curl of V is equal to 0. These small oscillation generated flows. And then we can go into Euler's equation, dV dt equals minus gradient W, and just continue on with what I had before. Gradient d phi dt plus W is equal to 0. Therefore, and again, I'm just exchanging in differentiations, okay? Here I made use of the fact that here, V equals gradient phi x, y, and z, and t, like I had before, okay? So that I have, plug that in, get that, and then d phi dt plus W is equal to a function of time. And interestingly, we're never going to actually have to know this function of time, because we can always think of it as being absorbed into the time dependence of phi itself. Okay? So it equals a function of time, and so this is an important result. You know, it's here in the corner, the way they sometimes end up. For incompressible flows, then we can have the d phi dt plus plus v squared over 2. I didn't do it. Hope that doesn't happen again. I guess we'll cut this, call this right now before something else happens. Gonna fire alarm there. Yeah, you know what I'm gonna do is consider this proof to be completed up to here. Okay. And we'll pick up with this next time. What we found was, so yeah, it's not that we're going to strike this from the record, but we'll start with this next time. What we found was oscillatory motions, generated by some oscillating solid, or, for example, generate a curl-free fluid flow field. And what that allows us to do is express the velocity field as the gradient of a potential, which is a huge win, very important thing for the theory. Good, that's what we're going to call it right now, and then we'll pick this up next time. Good, see you guys next time.